Hello my beautiful PU2 students. I guess you people are preparing well for your pre-board examination, right? So if you have done any kind of mess or you are not satisfied with your pre-board examination, please don't worry. Still now you are having time, focus on your study, boost up your knowledge and keep preparing yourself without diverting your mind. And please make sure you are doing all the model paper properly without leaving a single question. So that's the reason today I am here to help you out with the model paper 3. So yes, today our target is to complete analysis of model paper 3. So without further delay, let's start it. Before starting, just let me tell you, my dear students, if you are also preparing for the KCET, then our Deeksha Karnataka channel is here to take you to the top 1000 rank in KCET if you enroll yourself in the ABHYAS KCET test series. So they are providing 35 mock test, along with that the previous year questions of all the chapters. Please enroll yourself as early as possible so that your preparation becomes at the top. So without further delay, let's get started with our model paper 3. So just a little bit analysis of the question paper. Question 1 to 15. That is MCQ type. 15 questions are there, 1 marker question, you know it. Question 16 to 20, this is the fill in the blanks type of question, that is also 1 marker. Next you can see question 21 to 25, short answer type question, 2 marker, 5 questions, right? Question 26 to 34, you will be having 3 marker question, okay? And total number of questions are 9 out there. You will be having options, okay? Question 35 to 40, you will be having large answer type, they will be of 5 marker and the number of questions will be 6. Now here you can see question 41 to 46, you will be having numerical type of question and that will be also 6 question out there, 3 you have to attempt, okay? But we are not going to miss out any single question here. So with complete analysis, let's start model paper 3. Okay, so section A, 1 marker. First question you can see. Select the correct option from the given choice. The common oxidation state shown by the element with atomic number 21. So atomic number 21 is basically scandium, right? So if you just write the electronic configuration of scandium, this is basically 3D1 4s2. So scandium will get very stable oxidation state if both the s electron and d electron gets eliminated. As a result of this, it will get that noble gas like configuration, and overall how many electrons are left? 3 electron, and hence you can see +3 oxidation state. Let's proceed. Here you can see which of the following is homoleptic complex. Homoleptic complex in the sense, in case your particular complex inside the coordination entity, you are having the same type of ligands attached with your metal. Okay, that is called homoleptic complex. Very important zone. So you can see option D. Here you are only having ammonia inside the coordination sphere, so option D is going to be the correct one. Next you can see the correct name of the reaction. So this is a name reaction where the halogen exchange takes place, and you can see you will get alkyl iodide out of it, right? So it's a Finkelstein reaction. Let's proceed. Here you can see the chemical formula of Hindenburg reagent. So basically it is benzene sulfonyl chloride. So it looks something like this. This thing, right? So your answer is going to be C. I guess it's clear. Let's proceed. You can see doctor advised a 50-year-old woman enough exposure to sunlight and addition to fish and egg yolk to her diet. Name the vitamin deficiency for the possible disease diagnosed by the doctor. So definitely some vitamin deficiency, as you can see the option, and I guess you people know like for which deficiency, which vitamin deficiency you need to get exposed to the sunlight. Yes, that is vitamin D. Let's proceed. Here you can see salicylaldehyde. salicylaldehyde can be prepared from which of the following reactant? Okay, so this particular reaction, if you just look at, it's a Riemann-Tiemann reaction. So if you just start with the phenol, next what you have to give? You have to give some CHCl3 and aqueous NaOH. I'm not writing the intermediate thing, I'm just directly writing the product. You will end up with orthohydroxybenzaldehyde or salicylaldehyde, right? This is my Riemann-Tiemann reaction. So option B is going to be the correct one. I guess it's okay. Let's proceed. Okay, so major product formed in the reaction. Okay, so here you can see alcoholic KOH. Alcoholic KOH indicates it will undergo beta elimination or dehydrohalogenation. Now here you can see, if I write the reactant, let me just write it in a different way so that you can understand it. Like this. Let me just mark the beta hydrogen. So these are the beta hydrogen, right? This is the beta carbon. This is also the beta carbon. So you can get two products out there. So first I'm just representing with green ink. You can see this will jump here, this will go. So as a result of this, the product you will get, it is something like this: CH3, CH, double bond, CH, here CH3. Right? Now another possibility is there, this also can come and then it can go like this, and as a result of this you will get something like that: CH3, CH2, CH, double bond, CH2. Okay, so these two possibilities are there, among which, let me tell you my dear, this is going to be the major one. Okay, why major one? Because of the Sayani rule. Okay, Sayani rule is saying that most substituted alkene is most stable. Why? Because of the normal hyperconjugation, right? So this is the most substituted alkene. You can see both the side you are having two methyl group attached to this alkene unit, but here this particular thing is less substituted, so that's gonna be the minor one. So now let's check what type of compound is this. This is 2-butene. So option D is going to be the correct one. I guess you understood this. Let's proceed. Here you can see statement 1 and statement 2. Benzylic alcohol, the OH group is attached to sp3 carbon atom next to the aromatic ring. Yes, absolutely true. So if you just draw this thing, CH2OH, this particular carbon is called benzylic carbon. This is called benzylic carbon, and definitely if you just look for the hybridization, it is sp3 hybridization, right? So definitely statement 1 is the correct one. Next you can see in vinylic alcohol, the OH group is bonded to a carbon atom of carbon-carbon double bond. Yes, that is also true, because if you just look at this thing, CH2 double bond CH-OH, okay, this particular carbon is known as vinylic carbon. And also this particular carbon has sp2 hybridization. So option A, I mean statement A and 2, statement 1 and 2, both of them are correct. So option A is going to be the correct answer. Let's proceed. Here you can see a reaction is given the correct rate. Okay, let's do it. So how we should write? Rate of the reaction is basically equals to minus 1 by 2 d of A dt is equals to minus 1 by 3 dB dt is equals to, see, here below 2, so it will go up. So minus 2 into dC dt. Now if you see that all the option, this particular side, you have to just multiply this particular coefficient to the other. So let's do the same. I will get something d of A dt equals to minus 2 by 3 dB of dt equals to minus 4 dC of dt. So that's going to be the correct answer. Option A, right? Option A is going to be the correct one. I guess it's clear to you. Let's proceed further. Here you can see this type of question, I guess whoever from the south zone, they face the same question. Okay, so just see lambda m, and it is there in the model paper, I guess, model paper 2 if I'm not wrong. Just correct me if I'm not, if I'm not. Okay, so let's just match the unit out there. So here you can see I am having lambda m. So this particular unit is something Siemens centimeter square mole inverse. Okay, E cell is basically volt. Okay, kappa is basically Siemens centimeter inverse. Okay, and G star is basically centimeter inverse. Let's mark them. So 4 is with B, 3 is with A, 2 is with D, and 1 is with C. Okay, so option B is going to be the correct one. I guess it's clear to you. Let's proceed. Here you can see hydration of acetylene, that is ethine, with H2SO4 and HgSO4. Okay, so if you are having acetylene like this, okay, now if you are giving H2SO4, HgSO4, then you will get one hydroxyl unit attached to it. So you will get something like this. So you can see this is an enol type of compound. Okay, see, one in, one all. This is an enol type of compound, and it will undergo keto-enol tautomerism. It will undergo keto-enol tautomerism. As a result of this, you will get something like this. That is your acetaldehyde, right? So yes, your answer is going to be C. I guess it's clear to you. Let's proceed further. Here you can see 10 ml of a liquid A and 20 ml of a liquid B are mixed at 25 degrees Celsius. The volume of the solution is measured to be 30.1 ml. Then you have the option. Okay, so 20 plus 10, if you do, it is 30 ml. But here you can see it is given as 30.1, means you can see delta V mix, it is little more, right? 0.1 more, right? So delta V mix is greater than 0, right? Delta V mix is greater than 0 when it happens? It happens when there is a positive deviation of Raoult's law. When there is positive deviation of Raoult's law. And that also indicates that the delta H mix must be positive as well. So your answer is going to be C. I guess it's clear to you. Okay, so here you can see arrange the following complexes in increasing order of the crystal field splitting. Okay, so you are having these compounds, right? Let me just show you the spectrochemical series, how actually the ligands are situated. Then it will be clear to you. Okay, so basically here what happens, Cn minus is the strongest field among them. Okay, after that it comes H2O. Yeah. After that H2O, after that F minus comes, then Cl minus comes. Now you can see the picture is quite clear to you. So yes, Cn minus, H2O, F, Cl. This is going to be the correct answer. I guess it's clear. More stronger the ligand is, then it will impact the d orbital in a better way, hence you will get the maximum splitting, right? So this is the correct order. I guess it's clear to you. Let's proceed. Here you can see a binary solution has two components A and B. The mole fraction of the component is a 0.5, then the number of moles on the component A and B in the solution. Okay, fine. So mole fraction of A. So mole fraction of A means XA. So XA you are getting 0.5. We know XA plus XB is basically 1. So definitely XB is also going to be same 0.5, right? So from here I can tell that NA is equals to NB. I guess it's clear. Mole fraction of both of them are similar, so from there I can tell that yes, both of them are present in a same number of moles. Let's proceed further. Here you can see the reagent which does not react with both acetone and benzaldehyde. Okay, so here Fehling solution is going to be the correct answer, because Fehling solution is a very mild oxidizing agent and it can't oxidize acetone, because acetone you can see it's a ketone, right? But benzaldehyde it's an aldehyde, so it will not be able to approach the acetone. Okay, let's proceed. Here you can see this is the fill in the blanks type of question. So Van 't Hoff factor for the non-electrolyte in the solution. So non-electrolyte, they do not undergo any kind of further dissociation, so it will be 1. Okay, so this is gone. Next, the actinoids generally shows +3 oxidation state. This is also gone. Okay. Next, the color of para-hydroxyazobenzene, that's going to be orange. That is also gone. Next, you can see the dash, the OH group is attached to the carbon, that is sp2 hybridized, so it's going to be orthocresol. Okay, next you can see the carbohydrates which reduce Fehling's and Tollens solution are called as reducing sugars. I guess the fill in the blanks portion and the MCQ is clear to you. So without further delay, let's proceed towards section B. Okay, so let's proceed with the section B, that is of 2 marker. So here you can see the first question, write any 2 differences between the order and molecularity of the reaction. So here you can see I have given so many differences among them, that is what is order and what is molecularity with respect to that. Any 2 differences you can pick out of it. Like you can put this thing that it is the sum of the powers of the concentration in the rate law, and in the molecularity it's basically the number of the reacting species, and you can say that it's a experimental determined in case of order, and in case of molecularity it is basically a theoretical concept that is derived through the mechanism. Like that, any 2 points you can proceed with. Let's proceed. Here you can see what are optically active compounds give the condition for the molecule to be optically active. So first, optically active compounds are those compounds who can rotate the plane of polarized light in the polarimeter itself. Okay. And the next thing, give the conditions for a molecule to be optically active. First is it should be non-superimposable mirror image, and nextly it should not contain any kind of symmetry element like center of inversion. So many symmetry elements are there, they should not contain any kind of symmetry. Let's proceed. Here you can see, write the products formed when anisole reacts with ethanol chloride in the presence of AlCl3. Okay, just let me show you this thing. So let's say I'm having anisole. Anisole means OCH3, benzene with OCH3, and I'm reacting with CH3COCl, that is my ethanol chloride, right? And here I am giving AlCl3. So this is nothing but Friedel-Crafts acylation reaction. Okay, and OCH3 is an ortho-para directing group. So definitely the acyl group will be attached in the ortho and in the para. So here you are getting OCH3 one, let's say it will be something like this, and another one you will get the para 1. I guess it's clear to you. Okay, let's proceed further. Here you can see with respect to the first transition element series, which element has first highest second ionization enthalpy and lowest enthalpy of atomization second. Okay, so highest second ionization enthalpy is definitely for copper, because we know the configuration, electronic configuration of the copper is basically 3D 10 4s1. So if you just give first ionization energy 4s1, electron will be lost, then it will get 3D 10 configuration. So definitely if you want to further ionize it, if you want to further remove one more electron, you have to give some more energy to it. Okay, and next is lowest enthalpy of atomization. Okay, how this concept comes? So you can see zinc is having no unpaired electron in it. It's 3D 10 4s2. Right, so as it is having no unpaired electron, so no interaction is present in between two zinc atom, right? As a result of this, it is having very low enthalpy of atomization. Okay, very weak interaction among two atom, two bond, I mean the bond between two atoms. So very low energy you need to break them and to make it a single atom. Okay, so the answer is zinc. Let's proceed. Here you can see, identify the proteins and give any one difference between these proteins. The protein present in the hair. So the protein present in the hair is basically the keratin one. Okay, and the protein present in the egg albumin, that is basically, okay, it's actually egg white that should be, and the protein present is albumin. Okay, the question should be given as egg white. It's directly taken from the model paper itself. So just a small correction, just it should be taken as egg white, and the answer, the protein present over there is albumin. So first difference that I can make out of it, the keratin and albumin, right? So first one, it is a fibrous protein, and this is a globular protein. That is a major difference. Okay, this is water insoluble, and this is water soluble. Okay, that's it. Okay, let's proceed. So let's proceed with the section C, that is of 3-marker question. So first question comes up with the write the balanced chemical equation involved in the manufacture of potassium dichromate from the chromite ore. So very important question. Please don't forget or don't miss out this particular portion from the D and F block. Both the preparation of K2Cr2O7 and KMnO4 is going to be important one. So here you can see the detailed process is given, it's written over here. So the chromite ore you have to start with, you have to treat it with sodium carbonate in presence of oxygen, right? You have to roast it, right? So as a result of this, you will get sodium chromate at first. Then what you have to do, sodium chromate needs to be converted to sodium dichromate. Okay, so what you have to do, you have to just treat it with sulfuric acid and you will get Na2Cr2O7. Okay, then what you have to do, you have to change the ion, right? So just treat it with KCl and you will get K2Cr2O7. I guess it's clear. Let's proceed. Here you can see, using valence bond theory, explain the geometry, hybridization and magnetic property of this compound. Okay, so here you can see the basic thing I have written over there. So just let me show you. Here if you just write normal cobalt 3+ configuration, so definitely it's going to be 3D6, right? So cobalt 3+ is basically 3D6. So if I just draw it something like this, 1 2 3 4 5 6. Okay, so this is my 3D orbital. After that, this is my 4s and this is my 4p. They are empty. Okay, but whenever amine will come, whenever amine will come, you can see under the influence of strong NH3 ligand, okay, because amine is a very strong field ligand and it will force pair the electron in the d orbital against the Hund's law. So if I just pair it up, so it will be something like this will go there, okay, 1, 2, 3, 4, 5, 6. So 2d orbital is now empty. Again I am having 4s and I am having 4p as well. So this is 3d, this is 4s, this is 4p. So now these 2d, 1s and p, okay, sorry. So these 2d, the s and entire p, okay, it will make the hybridization D2sp3. Okay, so the hybridization that is coming out, it is basically D2sp3. Okay, and as you can see, magnetic property, if you ask, there is no unpaired electron, that indicates diamagnetic in nature, right? Next you can see hybridization, okay, now you can see it is D2sp3, hence you can say it is of octahedral geometry. Okay, I guess the thing is clear to you. Let's proceed further. One more thing, just for an information I just wanted to tell, as you can see that d orbital it is using here, the d orbital is from the inner shell, right? It's not the nth d orbital. Nth orbital is 4. So if this particular hybridization would involve 4d, we could call them outer orbital complex, that is the nth d. But here you can see outer orbital is 4, but we are using the d orbital from the inner n-1 shell, that is 3d. So that's the reason it is also inner orbital complex. Okay, it is also inner orbital complex. Just for an information, just sharing. Okay, let's proceed further. Here you can see, on treating COCl3 4NH3 with excess AgNO3, 1 mole of AgCl is formed. Formulate the complex and write the geometrical isomer. Okay, just let me tell you at first, I am having 1 mole AgCl form. So definitely that AgCl came because of 1 Cl that is present outside the coordination sphere, right? Because whatever the Cl present inside the coordination spheres, they will not react, right? So definitely the compound is something like CO NH3 whole 4, sorry, Cl2 1 Cl outside. So now from here if you react it with AgNO3, okay, definitely you will end up with this particular chlorine will react with AgNO3 and definitely you will get 1 unit of AgCl precipitation. Okay, so this is the complex. Okay, as you can see, it is a MA4B2 type of complex. A4B2 type of complex, and hence it will show cis and trans isomers. Okay, so now here you can see this is the cis isomer where all the NH3 are at the same side, okay, and Cl at the same side, and here you can see Cl at the opposite side of each other. Okay, this is the trans one. Okay, I guess it's clear to you. Let's proceed further. Here you can see, write the formula of the 3 different type of compound formed when the lanthanoids react with the carbon or heated with carbon. So here you can see when they react with carbon at around 2500 or 2800 Kelvin temperature, they form usually carbides. Okay, so what type of carbide? They can form LnC2 type of, Ln2C3 type of carbides and Ln3C, this type of carbide. So that's gonna be the answer. Okay, I guess it's clear to you. Let's proceed. Here you can see, write the IUPAC name and the structure of this species and mention the number of bridge ligand. So here you can see it's very easy. Basically 8 carbonyl units are there, 8 carbonyl units, and overall it is a neutral ligand, and hence cobalt is going to be definitely 0 oxidation state, right? So octa carbonyl cobalt 0, that's it. Okay, next you can see that is the IUPAC name. Structure you can see it looks something like that. So these 3 carbonyl, and here these 3 carbonyl, total 6 carbonyl, they are terminal. Okay, and 2 carbonyls are there, they are bridging. Okay, so I am having 6 carbonyl compound as the terminal one and 2 carbonyl compound as a bridging one. Okay, clear? So 2 bridging carbonyl groups are there. I guess it's clear. Let's proceed. Answer any 2 of the following. Okay, we will answer every single question, right? Because you people are champion. I know after completing your paper you will also attempt more than the question that they are expecting, right, to ensure good marks. Okay, so give an example of inert electrode. Write the representation of half cell reaction for the bromine electrode. So here you can see platinum electrode, we can take an example. Any other you can take as well, gold, carbon. Okay, next here you can see this is the half cell, this is the cell representation for this, and the reaction that actually takes place over there. So Br2, it is in the liquid form, it gets converted to wait. So it takes up 2 electron and it gets converted to 2 Br minus in the aqueous solution. This is the cell reaction and this is how the cell representation looks like. Okay, I guess it's clear to you. Let's proceed. Here you can see, write the overall reaction of nickel cadmium battery and mention the anode cathode of it. So here you can see at anode basically what happens, cadmium in presence of OH minus means in alkaline medium it forms cadmium hydroxide. Okay, and at cathode what happens, nickel oxide I am having. Okay, it gets reduced to nickel hydroxide. Okay, so overall cell reaction, just add them. So cadmium plus nickel oxide in presence of water, it will give you cadmium hydroxide and nickel hydroxide. That's it. Okay, so this is during the charging. Okay, I guess it's clear. This is the anode, cathode, I guess it's clear. Let's proceed. Here you can see, derive an integrated rate equation for the rate constant of 0 order reaction. Okay, so we can start with a reaction. Let's say I am having this A is giving product. Okay, so for this particular reaction we will derive it. So it's very important, either 0 order or first order, anyone you can actually expect from this particular chapter. Okay, so from here let's proceed. I can write the rate of the reaction in the form of differential rate of the reaction actually, that is minus d of A dt, and from the rate law we can write, it is basically R equals to K into A power 0, because it's a 0 order reaction. So I am having equation 1 and equation 2. So now I am equating equation 1 and 2 because both of them are equal to rate only. Okay, so equating 1 and 2. So I can get minus dA dt is equals to K into something power 0 means 1, so that's I am not repeating. Okay, so now just a little bit adjustment. So I can write dA equals to minus K into dt. Next step I am doing it here, so I can proceed with integration. On integrating both sides, On integrating both sides, what you can get? Integration of d of a equals to integration of minus k into dt. Okay, so let's just take out the k because k is your constant out there. So minus k into integration of dt. So here I am actually putting the limit. Okay, so whenever time is basically 0, means reaction has not started yet. Okay, then the concentration of A, let it be A0. Okay, when time t equals to t, any random time, okay, let it be the concentration of A be AT. Okay, so out of that what I can get is integration of dA is normal A. From here I am getting simply, if I just put the limit, AT minus A0, right, AT minus A0, and here minus K into T. Okay, so from here you can see I am getting something like, just I am taking minus as common, A0 minus AT equals to KT. From here I can get T equals to A0 minus AT divided by K. So that's going to be your integrated rate equation for the zero order reaction. Integrated rate equation for the zero order reaction. I guess it's clear to you. Okay, please make sure that you are mentioning the detail of the abbreviation. What is A0, what is AT, what is K, and what is T. Okay, K is the rate constant out there, T is the time, A0 is the initial concentration, and AT is the reactant concentration at time t. Okay, let's proceed. Here you can see, okay, one diagram is given. Given below is a sketch of a plant for carrying out a process. First is name the process occurring in given plant. Okay, so here you can see this side pressure is applied more than that of pi. Pi is the osmotic pressure, right? So from here I can tell that this particular process where it is going on, it is basically reverse osmosis, right? Because pressure applied is more than that of osmotic pressure. This is the condition for the reverse osmosis. Okay, name any one SPM, that is semi-permeable membrane, okay, which can be used in this plant. So we can use cellulose acetate. Okay, next, give one practical use of the plant, that is for the definitely desalination of the seawater. I guess it's clear to you. Let's proceed with the section D, that is of 5 marker. Okay, so here comes the first question. So we have to identify A, B and C. Okay, so first let's proceed with A. So here if you just write the A, it will be nothing but CH3, CO, CH3. Right? Now further, if A is treated with NaOI, then you will end up with CH3, CO, ONA. Okay, that's going to be your B, and C is none other than your iodoform, that is CHI3. I guess it's clear to you. Next, let's proceed. An organic compound this reacts with hyaluryl chloride, gives the compound Q. Q on further undergoes hydrogenation in presence of PDBSO4, forms compound R. Write the equation involved in the reaction. Okay, so this seems to be, okay, this is a formula of basically benzoic acid. Okay, just count the number of carbon and oxygen and hydrogen, it will be similar. Okay, so now if I just proceed with SOCl2, so definitely I will end up with benzoyl chloride. I will get COCl. Okay, then what I have to proceed with, and along with that some SO2 plus HCl also I will get. Okay, these are the byproducts. Okay, here I have to give the reagent hydrogenation in presence of PDBSO4, that is nothing but the Rosenmund reaction, right? That is nothing but the Rosenmund reaction. Okay, so this entire COCl will be converted to CHO, that is benzaldehyde. Okay, so your P is benzoic acid, Q is basically benzoyl acid, benzoyl chloride, sorry, benzoyl chloride, and your R is basically benzaldehyde. Okay, I guess it's clear to you. Okay, so let's proceed further. So here you can see, explain Hoffmann bromamide degradation, very important, and discuss the coupling reaction of benzene diazonium chloride with aniline, give equation and the IUPAC name. Okay, chalo, one by one we will see. So this is your Hoffmann bromamide degradation, where what happens basically, if you are having RCONH2 type of compound, then one carbon less aniline you will get. Okay, so you have to treat it with Br2 and NaOH in presence of water and a little bit heat, you will end up with RNH2. That is your HBD reaction. Next, discuss the coupling reaction. Okay, coupling reaction, if you just see, let's say I am having benzene diazonium chloride. So this is my benzene diazonium chloride, N2 plus Cl minus, right? So let's just break it down so that you can understand the coupling process. N2 plus Cl minus. Okay, now you are having aniline, right? Yeah. So this is your hydrogen, right? So they will couple to give you one yellow colored dye. Okay. So this is the compound. So this is para-amino azobenzene. Para-amino azobenzene. Okay. So this is the coupling reaction. You will get a yellow colored dye. Okay. So I guess it's clear. Now next is write the IUPAC name of this compound. Okay, so IUPAC name is basically, here you can see N, diethyl. Now here you can see, if I just number this thing, so here I am having 2 carbon, right? So 1, 2, 3, 4, 5, 6. Okay. Sorry, mine should not be termed. So in my parent chain you can see I am having total 5 carbon. Okay, by default you can see it is I am having total 5 carbon system. So how you can name it? N, diethyl, then 3 methyl, in the 3 position I am having methyl, and then pentane, in the 3 position itself I am having the amine, right? So pentane 3 amine, that's it. Okay. So how you should name it? N, diethyl, then I am having, in the 3 position I am having methyl, then it is a 5 carbon chain system, pentane 3 amine, that's it. Okay, I guess it's clear to you. Let's proceed further. Okay, glucose is a monosaccharide and an aldohexose, fine. Which oxidizing agent should be used to bring about oxidation of only the aldehyde group present in the glucose? So we need a very mild oxidizing agent. We can use bromine water out of in this particular case, and you will end up with gluconic acid. That will tell you, yes, whatever the carbonyl compound, I mean whatever the carbonyl functionality you are having in the glucose, that is none other than aldehyde only. Okay, so here you can see you are having glucose. If you just give bromine water, then you will end up with gluconic acid. Okay, so that particular thing you can proceed. Next you can see, mention any 2 forces that stabilizes 2 degree and 3 degree structures of protein, that is intermolecular hydrogen bonding and van der Waals force of interaction. Okay, next name the type of linkage that is present in the dinucleotide by joining 2 nucleotides. So that is basically phosphodiester linkage that keeps the two nucleoside unit joined. Okay. Let's proceed. Here you can see explain Fittig reaction with general equation. You can see you can have aryl halide type of compound, put sodium in ether medium and you will get diphenyl, that is a Fittig reaction. Okay, next write the mechanism of the conversion of the methyl chloride to methanol. So this is basically an SN2 mechanism. Okay, let me do it for you. So let's say I am having methyl chloride, okay. So this is my methyl chloride, let's say. So now let's say I am having any kind of aqueous KOH I have given out there. Okay, I can give aqueous KOH. Okay, so what basically will happen? So OH minus will approach from the back side. Okay, OH minus will approach from the back side. Now what I will get? I will get one intermediate, because SN2 is a single step concerted mechanism, right? I will get an intermediate, that is basically a transition state you can call, not a so-called intermediate, basically a transition state. Okay, so in the transition state what I will get? So you can see carbon, hydrogen, this hydrogen and this hydrogen, they will be in the same plane. So the leaving group is about to depart, but not yet departed. Okay, and the nucleophile is about to approach, means about to form a bond, but not yet formed. So this is also delta negative. I guess it's not visible to you. Let me just change the ink. Let's do it with green. Cl. So that is del negative, and here OH is also having delta negative. Okay, so here this particular thing is basically penta coordinated transition state. So penta coordinated TS. Okay, so from here how I can proceed further? From here what will happen? The nucleophile will be making a proper bond and the leaving group will leave the system permanently, and the structure, the geometry will be little bit tilted. Okay, so the compound will look something like okay. So this is the entire mechanism for the process. So now from the methyl chloride you got methanol. I guess it's clear, SN2 mechanism. Next you can see how many stereo centers are present in butane 2-ol. Let's draw the structure at first. So the structure is butane, means 4 carbon. In the 2 position I am having OH. Okay, so these particular carbon, if you just look at, just let me just break down a little bit. If you just look at that particular carbon, means second carbon, then this carbon is having 4 different functionality. One is methyl, one is OH, another one is ethyl group. So this is basically my chiral carbon. So I am having 1 stereo center. So I am basically having 1 stereogenic center. I guess it's clear to you. Let's proceed. Okay, the next question, write the steps involved in the mechanism of the acid catalyzed dehydration of ethanol to ethene. So 3 steps involved, very important question. So first step is basically ethanol gets protonated, formation of the protonated alcohol. So what happens, basically OH2 plus is formed out there. Next what happens, that OH2 plus becomes a very good leaving group. So that leaves the system and one carbocation is generated in between. Okay. First, then what happens, basically hydrogen jumps and elimination of one proton takes place and it gets back its double bond. Okay, so these are the mechanism that you have to Right, 3 steps, 3 mark. Okay, now for this particular case, it's the oxidation of phenol, right? So you will get benzoquinone out of it. You will get benzoquinone out of it. Okay, and for this particular case, you will get both ortho and para substitution. So this is, let's say, OH, here also bromine, all the ortho substitution and para substitution. Okay, I guess it's clear to you. Let's proceed. Here you can see next question, explain Hell-Wohler-Zelensky reaction with chemical equation. So this is a explanation of HBZ reaction. So basically what happens, if you are having a carboxylic unit, okay, if you are having a carboxylic unit that basically this type of thing, and here you want to add one halogen in the alpha position of the carbonyl. Okay, so this is the alpha, this is beta further. Okay, this is the alpha position if you want to add one halogen. Okay, so in this case we use this type of reaction, HBZ reaction. What we use, we give Br2 in phosphorus and water, and as a result of this, in the alpha position you will get one halogen. Okay, so I guess it's clear to you. Next you can see, write the reaction for the conversion of toluene to benzaldehyde using chromyl chloride. Okay, using chromyl chloride, it is a ATAD reaction, right? Because looking at the reagent, you should understand what type of reaction is it. So this is the entire mechanism. You can see, you can start up with the toluene, you can treat it with CrO2Cl2 in carbon disulfide medium, you can get a chromium complex, and if you put some H3O plus, means aqueous workup, if you proceed with, you will end up with benzaldehyde. Okay, next you can see, name the gas used to facilitate the nucleophilic addition of ethylene glycol to aldehydes and ketones. So that is basically dry HCl. Okay, I guess it's okay, hemiacetal ketal type of thing you will get out of it, out of this reaction. Okay, let's proceed further. Okay, so let's proceed with the section E. It is of 3 marker. You can see it numerical problem we can start with. So here you can see, calculate the osmotic pressure of 0.5% weight by volume aqua solution of sucrose at 300 Kelvin. Okay, let's start. We can directly proceed with the formula, that is pi equals to I into M into RT. Okay, so let's just a little bit breakdown of the molarity. So if you do, that is basically the weight of solute divided by molecular weight of solute into volume of solution into 1000. That is a formula of molarity, right? Into R into T. Now let's put everything over there. I is going to be 1 here because it's a non-electrolyte, right? So 1 into weight of the solute. See, 0.5% is given, 0.5% weight by volume. It indicates I am having 0.5 gram of solute in 100 ml solution. That information by default it is given. So let's put the value. Weight of the solute is given 0.5 gram, okay, into 1000 divided by molecular weight of the solute, that is sucrose, it's given 342 gram per mole, okay, into the volume of the solution is given as 100 ml, right? 100 ml into R is given as 0.0083 liter bar mole inverse, right? Yes, into 300 Kelvin. Okay, so now if you calculate this entire thing, your answer will be almost equals to 0.0364 bar. That's going to be your answer. Okay, I guess you understood this. Just in a single formula, utilizing a single formula, you can do the entire process. Okay, let's proceed further. Here you can see the next question. Calculate the electromotive force of the cell. Assume the cell reaction at 25 degrees Celsius is given like this. Fine, we can directly approach the Nernst equation. E cell is going to be E0 cell minus 0.0592 divided by N log of product by reactant. So concentration of PU2 plus divided by concentration of Ag plus whole square. Right? Now let's put the value. 2.97 volt minus 0.0592 divided by 2. 2 is the number of electron transferred. Log concentration of Cu2 plus is given as 0.250 divided by 1 into 10 power minus 3 whole square. Let's proceed. So now if you just do it, 2.97 volt minus, if you just do this division, it will come as 0.0296, right? Now from here you can get, so this is, you can see 10 power minus 6, right? And above it is given as 0.250. So I can write it like log of 25 into 10 power 4. So if I just simply calculate here log of 25 into 10 power 4, how much it comes? You can see we can write log of 25 plus log of 10 power 4, right? So log of 5 square we can write, and plus here I am getting 4. So from here you can do 2 log 5, log 5 value you can put plus 4. If you calculate this thing, you will get it. Okay, so I'm just directly writing it in order, just in case you need to calculate the thing log 5, then log 25 into 10 power 4, then you can proceed in this way. Okay, anyway you will get the log table. Utilizing this, you can just put the value of log 5 and you can calculate. Okay, so 2.97 volt minus 0.0296 into log, this value will come as 5.3979. Okay, so now let's calculate. Sorry, the log will not be there. Okay, so now if you calculate further, then this will come as 2.97 volt minus 0.1598 volt. Okay, if you calculate this, almost your answer will come as 2.8102 volt. Okay, that is your answer. I guess it's clear to you. Let's proceed further. Okay, so here you can see a column containing 0.05 molar NaOH has an area of cross section 0.785 centimeter square, and the length of 1 meter shows a resistance 1.11 into 10 power 4 ohm. Calculate the molar conductivity. Okay, so from here we can calculate the cell constant, that is G star. So G star is basically length by cross sectional area. So L is basically given as 1 meter, so we can take it in centimeters, so that's gonna be 100 centimeter divided by cross sectional area is given 0.785 centimeter square. So if you calculate this, it will almost come as 127.3885 centimeter inverse. Okay, next what we can proceed with, we can just put the value of R. Okay, let's calculate kappa out of it. So kappa is basically equals to G star divided by R, right? So G star value we can put 1.27.3885 centimeter inverse divided by R is given as 1.11 into 10 power 4 ohm. If you calculate this, it will come as 0.011476 Simon means ohm inverse, right? Simon centimeter inverse. Okay. Now from here we can calculate lambda m, that is a molar conductivity. So molar conductivity is basically kappa into 1000 divided by C. Okay, let's put the value of kappa here. 0.011476 0.011476 Simon centimeter inverse. 0.05 molar solution is given. 0.05 molar solution is given, and 1000, right? 1000 centimeter cube per liter. Okay, so now if you just calculate this entire thing, your answer will come as 229.52 Simon centimeter square per mole. Okay, so that's going to be your answer. I guess it's clear to you. So this is your step 1. This is your step 2. And this is your step 3. Okay, let's proceed for the next one. Okay, a first order reaction has a rate constant 2.3 into 10 power minus 5 second inverse at 500 Kelvin. At what temperature rate constant of the reaction becomes 17.25 into 10 power minus 4? Okay, that's here we are going to use the Arrhenius equation. Okay, so let's put it. Log K2 by K1 equals to EA divided by 2.303 R into 1 by T1 minus 1 by T2. T2 we have to calculate, right? So let's put the value whatever it is given out there. So log 17.25 into 10 power minus 4 second inverse divided by another K is given as 2.3 into 10 power minus 5 second inverse, okay, equals to EA. EA also given, yes. Okay, we will convert kilojoule to joule. So we can take it as 191,472 joule per mole divided by 2.303 into R value, let's write 8.314 joule per Kelvin per mole. Okay, here 1 by T1 is given, that is 500 Kelvin, right? Okay, next 1 by T2 we have to calculate. Be careful about the calculation. Okay, so if you basically calculate this particular portion, this log wala portion, then you will get 75. Okay, so log 75 is basically equals to this entire thing, 191,472. So unit, let's cancel out. Mole inverse will be cancelling out. Joule will be cancelled out. Here I am getting Kelvin inverse, so that will also get cancelled out, right? So Kelvin inverse, from here also Kelvin inverse will be cancelled out. So I am having this unit divided by, okay. So now what I can proceed with, this thing is given divided by 2.303 into 8.314 Kelvin. Okay, so here I am having that thing 1 by 500 minus 1 by T2. Okay, so now if you calculate log 75, okay, if you calculate log 75, how it should come, you can see. Log 75 I can break it down as log 25 into 3. So log 25 I can break down as log 5 square into log 3. So now 2 log 5 plus log 3. So from the log table itself you can put the value of log 5 and log 3 and you can calculate this. Okay, so log 75 it will come as 1.875. 1.875. So let's multiply entire thing into 8.314 into 2.303 divided by 191,472, and here I am having 1 by 500 minus 1 by T2. Okay, let's calculate further. I am taking it that side. So from here if you calculate this side, you will get something like 0.0001874994 if you calculate that side. Okay, that is equals to 1 by 500 minus 1 by T2. So from here finally if you calculate 1 by T2, that you will get 0.001826 Kelvin inverse. Okay, so now if you calculate T2 out there, you will get almost equals to 551.77 Kelvin, and that's gonna be your answer. Okay, I guess it's clear. Actually sure, I mean it's a very direct numerical. You just have to apply the formula. Okay, just be careful about while you are just putting the values and calculating, that's it. Okay, I guess it's clear. Let's proceed. A first order reaction has half-life of 23 minutes. How much time will it be needed for 30% completion of the reaction? Fine, it's also an easy one. You can see T half is basically given out there, that is 0.693 divided by K. From here we can actually calculate K, that is equals to 0.693 divided by 23. So from here if you calculate this, it will come as 0.03013 minute inverse. Okay, let's put the value here in the equation in the integrated rate law. So T equals to 2.303 divided by K log of A0 by 80, right? So A0 here 30% completion means 80 is 70%. So full initially it was 100, now 70% is remaining. Okay, so now if I calculate 2.303 divided by 0.03013 minute inverse log 10 by 7, right? So from here log, you can just calculate it in this way, log 10 minus log 7, you can put the value out there. Okay, so you will get it as if you calculate this, you will get something 76.43 minute into this particular portion. The way I told you, log 10 minus log 7, if you proceed with, you will get it something like 0.15488. Okay, and if you calculate ultimately, your answer will come as almost equals to 11.84 minute. That's going to be your answer. Okay, I guess it's clear to you. Let's proceed further. Okay, so this is a question. Here you can see if solution obeys Raoult's law for all concentration, its vapor pressure would vary linearly from 0 to the vapor pressure of the pure solvent. Okay, calculate the value of X. Here I have to calculate, but here I can use actually this formula. P of solvent, pressure of the solvent is basically equals to mole fraction of solvent into P0 of solvent. Okay, so yes, so you can see mole fraction of the solvent I can get out of it 0.4 and P0 I can get 1.013, that will only give the value. That P solvent, pressure of the solvent is nothing but the X, this one. Okay, so from here I can get the value 0.4052 bar. That's it. Okay, so that's going to be the answer. Okay, so that's it. So we are done with the model paper 3 complete analysis. So please keep practicing the concept. Please follow the numerical pattern that is given in the model paper, all the model paper 1, 2 and 3, and make sure you are practicing the MCQ, because you can get your MCQ common as well from the model paper. So to get more such informative videos, so don't forget to like, share and subscribe our channel. Thank you so much. Thank you for being a part of this Deeksha Karnataka channel. Thank you.